talk about design patterns. Okay. All right. So let's talk about design patterns. So basically, the idea behind design patterns is that as our industry matures, it starts to accumulate a body of knowledge and experience of working over multiple projects over a long period of time, and as we work in so many projects, we start to identify certain patterns, right? And we start identifying things that worked well and things that didn't work well, and oftentimes we try to generalize, what were the factors that were successful and what were the factors that were not successful, and with the intent that next time that we identify the same pattern, we're not going to reinvent the wheel, right? That we can lean on past experience on what worked well in similar scenarios, and that if that solution worked well, maybe it might work well as well in this scenario, right? And a lot of it comes from just being around for quite a while and having seen tons and tons of different aspects. But ideally, we can create a culture, right, where we can write down this body of knowledge and leave it for the next generation, right? So that we can have folks just read and not have to have their own experience, right? They can just read and see if it matches this pattern, if a particular problem that they're looking at, to see if it matches that pattern, if someone else looked at this before. So then we don't have to reinvent. The idea is based on other similar aspects and strategies in other industries, such as architecture, that have been around much longer than computer science, and have accumulated a huge amount of knowledge across the centuries, and so they were able to lean on this body of knowledge, right, and talk with authority on what should they do, how things should be designed, and make decisions as if they know what they're talking about. Again, leaning on somebody else's, or being, standing on somebody else's shoulders, right, on giants. And I mean that's what humanity does. We are always the inheritors. We always inherit from the previous generations, and we build on top of that, right? And ideally, it just accumulates, and it's a self-feeding, positive feeding loop that gives us tremendous power technologically into the future as we get closer and closer to the singularity. So a lot of these documentation of these design patterns in architecture, make some bold statements, lots of very general statements about what seems to work. Everybody loves window seats, right? So these broad generalizations, perhaps that's true in certain cultures, but maybe not others. I don't know. But said bay windows and big windows with low sills are comfortable chairs drawn up to them, right? In every room where you spend any length of time, think about putting a window place. And here's a sketch of what it might look like. So we would like to do similar things in software engineering. Certainly other engineering fields have similar aspects, right, where they've accumulated body of knowledges and that they document them thoroughly for the next generation. Certainly experienced designers know from experience, right? what is it they say in one of the sayings in my culture says the devil knows more because he's very old, not because he's a devil, because he's been around just longer than everybody else, right? Anyway, so some of these standard design patterns have been collected over the years. One of the eminent standard bodies of work that was written a while back ago it's what is referred to as the Gang of Four book that captures many design patterns that are presumably still very, very relevant today, even though it's several decades old, right? It's still that's the idea, right? That you could make such generalizations that it's timeless, right? Regardless of what infrastructure, regardless of what particular technology you're using today, this still holds, right? This is a almost like a law, right? That we can appreciate over multiple generations. So a design pattern is a generalization, right, of a pattern that we've identified as a problem, right? That we can as a template, right? That we can identify that pattern and say, ooh, has somebody else already solved this, right? So instead of reinventing it, can we perhaps look at some specific solutions that might apply, some general solution that might apply to our specific problem. Okay. Now, a lot of the design patterns try to address issues that have plagued software engineering efforts for years, right? Some of them are the inherent characteristic of software that it evolves over time, right? That whatever code you're writing today, it might be that you'll come back to it next year or a couple months from now, and you have to refactor it in some way, right? And so any effort that you can make to make that work easier on you later on, right? Certainly is an investment well made, right? So how can you write code today, right, that would make it so that you can modify a year if requirements change, right? Or try to avoid writing it so specific to the requirements that changing it, to modifying it, would be a major redesign of the entire system, right? So many of these design patterns try to decouple a lot of those decisions and try to create decouple the concerns, right? Per role. What is the role of certain things? And try to encapsulate those roles and say, well, your role is to handle user interface. Your role is to store data. Your role is to instantiate new objects, or your role is to keep track of the life cycle of an object and things like that, right? And so identify what those roles are, right? And write them in such a way that you can replace them, right? Or you can extend them, right? And in such a way that you write them in such a general form that you can add to it without breaking the entire framework, right? Or architecture. The patterns somewhat have a schema on how they are documented. Typically, they have a name of a pattern. Presumably, it'll be some very abstract, high-level name that eventually will become vocabulary in the culture of software engineering. So that if anybody says, "Oh, I'm using an MVC," okay, so that everybody can kind of say, "Oh, yeah, I know what that is, right?" Model view controller. So that has become part of the lingo, right, of the culture within software engineering. And if I say that, well, all sorts of ideas come to mind, right? Already, lots and lots of architectural designs come to mind without me going to any specifics, right? And we understand what the consequences are of choosing that particular architecture, right? And similarly, these design patterns will, over time become part of the lingo of software engineering, so that if somebody says, oh, it's the abstract factory pattern, it's a Singleton pattern, if it's the command and control pattern, right? Immediately, lots of ideas and structures come to mind, right? And as we apply those design patterns in our source code, that also will help us collaborate in our effort. So that if somebody comes and looks over your shoulder and looks at your source code and looks at it, what are you doing? Oh, I'm applying the abstract factory patterns. Immediately they'll think on, oh, okay, you have 3-4 files around, you have a constructor, you have an interface, and they're already thinking of how you're structuring this, right? And so that we can manage a particular problem that might be 5, 10, 20 lines, 20 files, but at an abstract level. Okay, so I don't have to know the individual files. I already know how they're structured and how they're related to one another. Make sense? So just like we say, oh, it's a controller. Well, okay, well I know where the controller is and what it is, and presumably there's some view that's sending some events, right? And so a lot of these things come to mind. So ideally, these patterns will elicit that kind of lingo, that kind of ideas. So a name and also the pattern of the problem that it's trying to address. Usually, it'll diagram what the problem might be, right? Using some class diagrams. And so it might say, here's a particular organization of classes. It'll say what's wrong with that general problem, right? And then it'll maybe provide an alternative class diagram that says this is a better implementation of that class diagram, right? It'll introduce certain interfaces. It'll introduce certain additional classes, and then it'll explain why is it better, right? And says apply this pattern in these conditions. If the following are true, then this is a candidate for applying this pattern. Okay, and also the consequences. Sometimes you also have anti-patterns, of what not to do. Right? It says, this is a very common mistake. So it'll show all sorts of anti-patterns on what not to do, right? And hopefully none of your decisions might be one of those anti-patterns, right? Again, trying to capture where folks in the past have painted themselves in a corner, right? And it has been so common that it was worth documenting for other folks not to do the same mistakes. These patterns fall into various categories depending on the type of problem they're trying to solve and what level of abstraction they're trying to solve the problem. Some that are very, very broad design patterns, such as model view controller, for instance. Right, that's kind of like an architectural type of pattern, right? That encompasses large applications, right, and kind of makes you think on if you're thinking of any one artifact or piece of code that you're working on, where would it fall in any one of these three buckets, right? And what are the different roles that it's trying to solve? Some of the other ones are a little. Most of the design patterns are not that overarching. Some of them are either dealing with structural, creational, or behavioral problems. So the purpose might be creational, concerned with how things are instantiated and released, and managing the life cycle of objects. Right? We are nevertheless writing code that is instantiating objects, right, to represent and represent some values, some objects and relationships. Yes. And all this is transient. At some point, they're going to be released. We're not, and so what is the best way of doing this? Of instantiating and releasing? Who should be responsible for creating things and releasing things, right? And so usually that's a big issue, a big problem on who should call the new constructor, right? Who should be responsible for that? We've seen over the last decade or so, we've seen how component technology has dramatically changed that, right? And who is responsible for instantiating things? If I want to connect to a database, how do I get a connection to the database? Do I instantiate it? Right? We've already established that that's certainly not a best case scenario. Typically it is the infrastructure who instantiates it and somehow gives it to you, right? So you don't want to be responsible for that. Somebody else is responsible for it. You're just magically past this connection to a database. Same thing for security. Same thing for multi-threading. Same thing for many decisions. Who should be responsible for multi-threading? Do you want to be responsible for multi-threading? Usually not, right? Usually there are other services who are responsible for the life cycle of the thread that is running through your code. Or who should handle security? Do you want to handle security? Typically not. Typically is the infrastructure somehow already validated whether you have access to a particular method or not, right? So these many of these design patterns try to decide who has the responsibility to do what, right? And how can we design it in such a way that we can modify it, going forward. Structural, how is it that you combine objects together that are going to collaborate together to achieve something in common. Behavioral on how you're going to distribute the multiple responsibilities throughout the source. Also on whether you are dealing with class level or at the object level at a particular instance, or are you talking about a class at a higher level, right? So they can be classified in these two dimensions, that the Gang of Four classifies them at the scope and also the purpose in this table. And these are all the design patterns that they have documented in their very famous design patterns book, the Gang of Four books. And so here's many of them that today are still, most of them are still relevant today. Since then, obviously, there have been written many more books that are specific to a particular infrastructure. So certainly you can find books written specifically for J2EE design patterns or for .NET design patterns. Okay, that are usually variations of these design patterns, but specific to be applicable in the J2EE space or the .NET or in many different infrastructure. Okay, and I welcome you to explore these books. So let's look at some of these patterns. We'll first look at the creational patterns, right? And they deal with the responsibility of managing the life cycle of objects. Who should be responsible, and what are the best strategies of creating a new instance, right? We've already established that oftentimes we don't want to be the responsible for instantiating things. Instead, we prefer to delegate that to other folks that might be more knowledgeable on how things should be instantiated, right? The example of the data source, right? Do I want to instantiate a data source? Usually, I will want to get a hold of some class, right, that instead manages the life cycle of data sources, right, that connect to a database, right? That gives me an interface that I call on them and says, okay, will give me a connection. So create for me a connection, yes, and then that method will be smart enough to decide whether indeed it needs to instantiate a new one, or if there is or it might already have a pool of connections ready to go, a cached number of connections, and if there's one available, it'll, instead of instantiating a brand new one, it'll give it to me, right? So that there's no overhead of having to instantiate and connecting again to a database, right? And now I get the connection. right? And what the client who's using that connection didn't have to have this very complicated decision on whether to instantiate or not instantiate. Instead, it delegated it to somebody who has the knowledge to be able to make that determination. Make sense? Right? This pattern is a very common pattern, right? It's referred to as the factory pattern. Somebody knows how to instantiate these things and make these decisions for me, right? And that knowledge is complicated enough that it should be centralized into one single place. Okay? So creational patterns encapsulate the knowledge about instantiating concrete objects, right? That's another pattern that we'll take a look at. When I get back that object, that connection, right? Usually that connection that I get, usually it will be some kind of abstract connection, because that connection might be an SQL connection or an Oracle connection or a MySQL connection, yes? And I don't want to have to know what type of connection it is. I just want to know that it will have the same 4 methods, right? That I can create a SQL statement, I can execute a query, I can execute an update, right? And that's it, right? And then I can close the connection and that's it. Right? Me as a client, I don't want to be burdened with having to figure out whether it's one or another, right? So instead, what I get is some instance that implements an interface, some interface, yes? But instead, the factory will be delegated of deciding what instance I get, right? Based on some configuration, based on some property files, right? Or based on some other external things that are not privy to the client. Yes? So same thing. That knowledge is encapsulated in factories, either factory methods or factory classes that are responsible for managing these life cycles. Okay. All right. So let's talk about a couple of them. Yeah. So here's just a few of the creational design patterns: abstract factory, builders, factory methods, prototypes, and Singleton. So these are just a few of them, and we'll be covering some of them. So as a running example throughout the lecture, we're going to be considering this abstract problem, a toy problem of creating a maze, a game that can generate on the fly mazes that have rooms and doors and walls, right? And it creates a data model, a representation of a maze that presumably you can then navigate and try to get out of, right? To enter a room through a door and either turn right, left, and face a room to any one direction, north, south, east, west, and so we'd like to design it in such a way that it can be extended. Right? We'll first look at a first implementation, and then criticize it and say, well, what's wrong with this? How can we improve the design? Right? And usually the design will be that the improvements will be that can we generalize and apply some of these creational patterns and see what would be the consequence of applying that pattern, right? To try to generalize it so that it can be extended later on. Right? So that one of the first things that we'll come up with says, well, our first design is very static, that it cannot be easily extended. If we want different types of doors, of different types of rooms, of different types of walls, of different types, the first design will not let us do that easily. So here's the first class diagram capturing the various the data model, right? You have a maze that contains multiple rooms. There's a one-to-many relationship. A maze is made up of multiple rooms. A room can have multiple sides. It has a north side, the south side, east, west. It also has a couple of static elements here, such as room count, right? That every time we instantiate a brand new room, it'll count how many rooms we have, right? And that will be used to initialize the room number, right, from this static counter. And we also have a couple of functions of methods in here that allows us to either enter the room and also define the room by adding either walls or other rooms or doors to the room in a particular direction, either north, south, east, west. Okay? And notice that the room here is extending or inherits inherits from map site. Right, so map site is a base class that is a base class to the room, the wall, and the door. So a room itself is a map site. It's map site, so that a room can be next to another room, right? So that we can have a room to the north side of one room. You can have another room, okay, or to the side or the east or the west. So you can have rooms right next to each other, and they can link to one another, right? Also notice that we have a 1 to 4 relationship, right, where the room can have any 4 map sites, right? So you can have maybe two walls and a room and a door, right? Or maybe it could be closed, right? They're all walls and you can't get out of it. Or it could be just one door to one side plus 3 walls on the other side. So the other map site, we have the wall that again you can enter. Notice that they all have the enter function, that they're overriding from the base class map site. Plus, additionally, they have other functions, other methods that are specific to walls and doors and whatnot. We also have a kind of like a Singleton class up there that is the maze game that can instantiate instances of this maze. All right? Okay. So first we'll implement it as is, the way it's described in this UML diagram. Yes? And we'll come back to it and revise it, adding new design patterns and see what the consequences are. So here's our first declaration of the maze, having methods that allow us to. You have the constructor that once we create the maze, it just instantiates and prints that we're creating a maze. Also, it has a field that is a hash set of rooms that are going to allow us to just add any number of rooms. Ideally, it'll be just it can be any number of rooms. So a maze can be any number of rooms. You can add a room. First, it checks to see if it already has that instance of a room. If it's not already there, it adds it to the set. We have here the map site. So this is the base class from where everybody else is going to inherit. Notice that it's abstract, so you can't actually instantiate map site, right? You need to instantiate the derived classes. We also have an enumerated data type that declares north, south, east, and west, so that we can declare the direction, right, of a particular wall or door or room. Here's a room that extends from map site, and we have a constructor that increments a static variable room count. Room count is static, and it's initialized to be 1, and we use it so that every time you instantiate a new room, increments it, and it assigns the value to the room number, right? So every room knows what its number is, and it also, a room is made up of 4 sides, right? And the north side, south side, west side, and east side, meaning that the north side could be actually another room, right? Or could be a wall, or could be a door, right? So notice that room itself is a map site, right? So a room could have another room right next to it. We also have a toString, so that if we display an instance of this room, it will print with the room number. Additionally to this, we have the two methods that allow us to add each one of the sides, right? We can add either another room or a wall or a door in a particular direction, right? If the direction is north, it updates the north side or the south side or the east side or the west side. Okay. The get side, you can give it the direction, and based on that direction, it would return either north, south, east, or west, or null if you pass it something weird. All right, so these are the other ones, the wall and the door, right? That also have in their constructor a static counter, right? So that every time we instantiate it, it just counts how many walls there are, and it assigns it to the number, and just has a toString so that we can print it. Door, similar, it has a constructor that can take as arguments the rooms that it connects. Right, so you can go from one room to another room. So the door, a door is always between two rooms. Again, it has a counter and initializes the rooms that it connects, and it has as member variables room 1 and room 2. Okay. Notice that it's room, not a map site, so it can't connect the wall. It can't connect. It has to be a room. It can't connect walls. It can't connect other doors. It has to connect two rooms. Okay. It does not have the default constructor. Typically, you would also need the default constructor, but we've skipped it here for brevity. So here's a MazeGame. MazeGame has a function createMaze, and just randomly instantiates a new maze, creates a couple of rooms, creates a door, adds the rooms to the maze, and then it just goes on creating several walls, several doors, and connecting them together. So this is an arbitrary maze, right? And you can imagine that this could be randomly generated, maybe from some seed, and you can randomly just hook up multiple rooms, perhaps validating that no room is closed off, right? That you can't have four walls, right? That you need some way of getting out, presumably. Yes. All right. So there we go. So here's the client. This the client instantiates the maze and calls game.createMaze, and it prints out all the doors that it created, all the walls, and how they're connected to one another. Make sense? Right. We're not rendering any of this, right? But presumably you can extend it any which way you want. Anyway, so let's take a look at the object diagram. This is the instance of what instances were created. We created, let's see, a door that connects two rooms. So we only have two rooms, and door 1 just connects room 1 and room 2, and the maze is made up of these two rooms, and each room has to the various directions in the north, the west, the south, and west and west, east and east. Does that make sense? I think this might be flipped. Or this is west and this is east. Anyway, so this is the instantiation of the current objects as they appear in memory. All right, so what's wrong with the implementation? Well, I mean, it could be that that's all we needed, right? And that's fine, right? And it might work for a couple months, and once, but it turns out to be a hit, right? And people love it, and people start asking for more, right? And so this became a business opportunity, and we want to make it even more interesting, right? Maybe we want to introduce all sorts of new types of walls and different types of doors and different types of rooms that, depending on how you go, maybe you want to have a room that if you walk into a room, randomly you disappear and you appear in a completely different room, right? Just to make it more interesting. Or that if you walk up to a particular door, to open it, somehow you need to have a particular key. And so you might introduce certain different aspects to this, right? So as it stands, the program doesn't allow us to easily modify it, since it depends specifically on instantiating certain types of walls and doors and whatnot, and making those relationships. So if we want to extend it, perhaps different types of doors, different types of rooms and whatnot. Currently, it doesn't make it easy for us to just add, a plethora of different types of rooms and different types of walls. If we would want to, we would have to just create, individual classes, right, and instantiate them individually. We would be responsible for the instantiation of each one individually, and we would have to know the data type of each one of these classes. So it's not easily extensible without making a complete rewrite of the Maze game. So how is that we could rewrite it to make it less dependent on what the data type of the walls are, or the doors, or the rooms. So one of the things that we could do is that we can delegate the instantiation of these of each one of these objects, right, and use design patterns such as factory methods and abstract factories, so that we're not necessarily responsible for instantiating these things. We can abstract it. So it's sort of like if this were like a drawing program, right? And you have different widgets that you can draw on the screen. Maybe you draw rectangles and triangles and circles and just throw. And typically, what you want to be able to do is not have to deal with the plethora of types of shapes, and so that you introduce object orientation, right? You create a base class of shape, right? And then each one of these shapes, the different specific shapes, inherit from a base class, and they all instantiate, they all implement their draw function, so that you can use polymorphism, right? And polymorphism is a very powerful technique that allows you to write your code in a very general sense, right? So that if you want to draw, you just call draw, and it iterates over a collection of shapes, as opposed to let me draw all the rectangles, and then iterate over the circles, and then iterate over the triangles, and then iterate over. Instead of doing that, you would like to have one single big bag of shapes, right, and iterate over just that one big bag of shapes, as opposed to iterating over multiple types. Yes, right. So same thing here. Can we write it in such a general form that we're not dependent on each type of door and each type of wall and each type of these, and then we can easily just extend any number of shapes. Any number of walls and whatnot. So we'll introduce several of these design patterns, prototypes, and singletons that will introduce these generalities, right? That will allow us to abstract the different types of actual instances. So let's look first at abstract factory. So factory is going to allow us to delegate the instantiation and the life cycle of objects, so that we're not going to be responsible for instantiating them. Just like we don't want to instantiate a MySQL connection or a SQL connection or an Oracle connection, we don't want to do that. Instead, we delegate that to a factory function that is called maybe getConnection. Right? In that getConnection, right, we're going to concentrate the logic, right, of whether we're going to instantiate one or another instance. And what we get back, instead of a SQL connection or a Oracle connection, or we don't want to know the type. We don't want to know the type. Instead, what we get is a connection object. Right? I don't know what type it is, really. Right? I only get an interface. And some concrete class is actually implementing that interface, right? But me as a client, I don't want to be responsible for that. I don't want to know, right? So what the abstract factory allows us to do is implement that delegation. Somebody's actually going to have to do it, obviously, right? But we want to do it so that from the client's point of view, I'm not responsible for it. So when do we want to apply this factory? Is when we want to delegate the handling of instantiating multiple instances that are related classes that are slightly different from one another, but implement the same behavior, right? Like a connection, right? Or widgets on a screen, right? If we draw, we have if we drag multiple widgets on a page, right? Each one will have different behaviors, right? But they can all be draggable, they can all be repositioned, right? They can all be resizable, right? They all have similar behaviors, right? And I don't want to have to deal with each individual behavior differently. So here's a class diagram that documents the design pattern, right? Typically, notice that on the top left we have the client. The client currently, right, the way it's implemented today, the client is directly instantiating these concrete products. It is directly instantiating walls. It is directly instantiating doors, right? It directly is instantiating these things, right? Right. So what we want to do is that I don't want to have to do that. Instead, I'm going to have an intermediate, right? That abstract factory, right? Who I'm going to delegate the creation. So I don't want to do it. I'm going to delegate it to somebody. And that somebody is going to know what to do. And once I instantiate it, I don't want to work with the concrete door or the concrete wall or the concrete wall. Yeah. Or I don't want to deal with a specific type of product. Instead, I'm going to deal with an abstract product, right? A map site. But I don't want to know if it's a door specifically, right? So the way it will work is that the client asks for the factory. The factory that they get is either an actual concrete factory that knows how to instantiate the concrete products, okay, or a concrete factory 2. But the client doesn't actually know the real. And this is a design pattern that you see, more specifically, you see it very well on, in JDBC, right? It's very, very common, right? That you get a driver, right? A connection driver, and you don't know if it's a connection driver to any one of the underneath underlying infrastructure. Same thing with if you're doing messaging, right? Messaging between multiple systems. Typically, you have queues and you subscribe to a pub sub, right? And there are multiple implementations of this, right? There are many vendors who implement the pub sub or queues and whatnot, and you don't want to know the actual vendor specific implementation, right? Instead, what you get back is an abstract factory that gives me access to a queue. And you don't know if that queue is this vendor's queue or that other vendor's queue. You don't want to know. Instead, what you get back is an interface or some concrete class that implements the interface. But there's no way for you to know who the actual concrete class is, and you shouldn't care as long as it implements a particular interface. Yes? Again, the factory pattern is very widely used. Same thing for managing transactions. Same thing for it's a very, very widely used design pattern, and it's documented this way. You get an abstract factory that gets back a concrete factory that implements that abstract factory, and it's responsible for instantiating these products that implement some abstract product interface, right? That you get back in the client. The client doesn't know the underlying implementation. So these are the participants, right? You have the client uses only interfaces, abstract factory and abstract product. We have the abstract factory is a base class that provides the interface on how to instantiate something, right? That it's implemented by the concrete factories. You might have multiple concrete factories. Which one, typically depends on some configuration or some parameter that you pass in, right? Typically in J2EE, typically is configured through either a properties file, right, or some POM file, right, or some configuration that says, oh, this is the driver. The driver I'm connecting to this particular vendor, right? And then it figures out, by dynamically, it figures out which libraries to use to connect to the actual class. So here's another implementation using another idea, another concept of some abstract graphic user interface builder that this library could abstract could be a library that could be used in multiple multiple frameworks. It can either run on Windows, it can run on a Mac, and you can have multiple implementations, maybe on iOS, right, on Android, and you can imagine that you can have multiple implementations of a button, right, or any widget, right, any widget that you might think, maybe a drop down, right, or a date picker, or any widget you can think of, right. What you want to do is create multiple products, right? Whether that product is a button or date picker or any of a plethora of widgets. These would be the concrete products, but then you would have some abstract product that would be the base from which you inherit. So you have this abstract button that then are implemented either as a window button or a macOS button or an iOS button or as an Android button, right? And you like to be able to use this library, yes, independent of the framework. You don't want to know that you should instantiate it this way for Mac, or instantiate it this other way for iOS, or instantiate it this other way for Android. Instead, you just want to say, give me a button, right? I don't want to know what the details are. So what you do is that you grab a factory and an abstract widget factory, right? That would allow us to implement different factories implemented for different frameworks. So here's a concrete representation. You have perhaps an interface that implements some kind of abstract button, right? And a factory that knows how to instantiate these abstract buttons, right? And underneath, you would have the concrete actual instances that know how to build a Windows button or a macOS button or an iPhone button or an Android button, right? They would all inherit from these factories, the Windows factory and the OS X10 factory and the iOS factory and the Android factory. They all inherit from this high-level GUI factory, right? And here's where you implement the actual creation of these buttons. Whatever the details are would be hidden here from the client. The client would not see this. The client only sees the create button function, right? That implements the interface of the GUI factory. Obviously, this GUI factory would have create button, create date picker, create input field, create text area, create whatever drop down. It would have a plethora of all the create functions for creating all the different widgets. Yes, each one with its concrete implementation and interface. Here are the concrete products, right? The window button and the OS X button. Each one all implementing the overriding and implementing the base function that is declared in the interface. As long as we all agree that we implement the same interface, we're good, right? Where things might get problematic is that hardware might be different, right? That your interface doesn't accurately, by definition, is written to the lowest common denominator, right? That the behaviors are equally supported across multiple platforms, right? That if there's a new feature that either iPhone or Android comes up with that is not represented in the interface, right? Then you might have problems, right? and that's one of the reasons, presumably, that Apple, as part of their licensing, they would disallow these generic libraries that would allow you to write one user interface, right, and then deploy to both Android and iOS and multiple frameworks, right? This was a problem early on in the iOS, right? But I think they've abandoned that kind of licensing and that kind of restriction today. They do allow all sorts of libraries, that, IDEs, that to compile down to their own libraries. So anyway, so from way up in Maine, depending on the appearance, whether it's OS X or Windows or Android or iOS, typically you would then you would get the correct factory, either the OS factory or the Windows factory, and then use the factory to create the button. Typically, this would not be done here in the driver. Typically, it would be done outside in the infrastructure or configure in some properties file or XML document, right? That would configure the settings. And by the time you got here, you already would have the factory. Yes. So anyway, so let's apply this same idea to our toy maze application, where instead of us directly instantiating the maze, instead we are going to do it through a factory. We would instantiate the factory, right, and then we would pass along to the create maze. We pass the factory that we want to use to create the doors and the walls and whatnot, right? So the factory presumably has all these methods in there, right? That allows us to create each one of the widgets. Each one of the elements in the maze, right? Instantiate a door, instantiate a wall, and whatnot. So the create maze, we use the factory to instantiate the maze, to instantiate the doors, the rooms, and then it would add to the maze each one of the rooms, right? And so we would rewrite the original create maze in terms of using these factories, right? Of instantiating the walls, the doors, and whatnot, and then just returning the maze, right? So if we implemented this implementation, it would be now easy to extend this, right, and implement a different type of maze, right, where we could inherit from a base maze factory, right, and then we could either override some or all, right, or only a few of the instantiations that right, we could override only the rooms, or we could override the doors, and we could either inherit all the base implementation, or just override certain aspects of the functions, right? So here now we have the enchanted maze factory would inherit from the maze factory and override one or all, right? If we only want to enhance the implementation of rooms or only the doors, we could just override those, plus add new functionality, right? That to be able to enter a particular room, perhaps you need to cast a spell that was not originally in the factory that we had earlier, right? So now the client would not directly the client as we implemented earlier, right, would not directly instantiate it, would use a different factory and pass that factory in there, right? Also, again, typically it would not be this decision of which factory we're using. Typically, would be done in the infrastructure, right? That usually would be injected, right? So that the infrastructure instantiates it, and it's auto-wired and injected into the client, as opposed to us. So that would be another design pattern, right? Doing some inversion of control, right, and letting the infrastructure decide that. Notice that we didn't go all the way. We didn't go all the way with the design pattern. Notice that we did not, like we did for the widgets, we didn't make these abstract, right? So we didn't actually implement the entire design pattern, and right. So the maze factory overrides some or all the methods. Yeah, we didn't abstract. We certainly could have abstracted. Now, so because we didn't create the abstraction, right? If you want to use some of the original methods that we didn't override, you would need to probably downcast, right, to use some of the functions that are declared in the base classes that we inherited from. Okay, but we're going to be combining this design patterns with other design patterns that we introduced earlier, right? So we'll take a look at the Singleton design pattern, the prototype design pattern, and also the factory method design pattern. So typically these methods that we introduced earlier, typically that is they're actually implemented with another design pattern called the factory method design pattern, right? So it's very similar. It's going to be slightly subtle. The difference is going to be very, very subtle, since these two design patterns are very, very tightly related to one another. And the idea here is that oftentimes you're not going to know, or you don't want to know, the actual class type that you're going to use to instantiate. You want to leave that open to decide that at runtime, right? As opposed to, like here, we are deciding these instances at compile time. You want to perhaps leave it as, using late binding or dynamically bind into these libraries or to these instances at a later time. So in the creator pattern, which is oftentimes part of the abstract factory pattern, it looks very similar. We have the product that we want to instantiate, and which which a concrete product is inheriting from that product. So that product would be an abstract product, and to instantiate it, we use a concrete creator, and that inherits from a base creator, right? So we would instantiate the abstract creator to we would call the create product that would instantiate the concrete product. We would really only get the abstract product. So we won't have direct access to the concrete instance, right? Only through the interface. So this is very similar to what we just did. So let's take a look. Where is it? So let's rewrite the create maze from the maze game using the factory method. So let's look at it. So the maze game instantiates these concrete instances of maze and room and wall and doors. So you would have each one of these instances, so that so in the create maze you would call these functions that would instantiate, right? And any logic of deciding how to instantiate them would be encapsulated in each one of these functions. Now, typically these make maze and make room and make wall would be part of the factory. The factory would be the one who's responsible for encapsulating all these functions. So typically you combine these two ideas together to create an abstract factory that uses factory methods. Okay. So this rewriting the enchanted maze game, you would extend maze game, and then you would inherit and override the implementations of each one of these factory methods, and use the enchanted maze game. So instead of using the factory, right, and then passing the factory to the create, here we're using directly those functions that create them. Usually the abstract factory and the factory methods are used to implement the abstract factory. These two design patterns work together. So another idea is to use prototypes, right, where we instantiate one of these objects, right, and then instead of reinstantiating every time, what we do is that we clone a pre-existing instance of an object. Especially if these are objects that are very expensive. Perhaps these are objects that need to read from a file system, or maybe do a network connection, or do some long-running computation to initialize themselves, and they're very expensive to reinstantiate, right? So typically, what we try to do is avoid calling new on them, right? Or maybe you would call new on them only once, right? Perhaps when the server is booting up, right, and it's doing a long-running set of tasks while it's booting up, right? So during that time, it can call new on multiple very expensive objects, have them initialized, and once it's running, right, it keeps these objects around, right? And whenever you need to use these objects or any new instance of these objects, instead of instantiating a brand new one, it clones, right? It clones or copies the memory onto a new instance, and then it gives you a reference to this new instance, which is much more efficient than reinstantiating these objects, right? Typically what we do is that you clone the object and then you do minor changes to that object, right? So that it would maybe behave differently, right? But where most of its state is the same as the original prototype object, okay? So prototype allow you to avoid. Also, typically when you have objects that have a fairly deep inheritance hierarchy, right? Where you have base class and then extend. You have a long chain of inheritance. Oftentimes, the factory design pattern typically follows the same parallel implementation of that inheritance tree, right? So it becomes fairly complicated, to keep track of these two parallel inheritance trees, right? So as an alternative, instead of using the factory pattern, the prototype, you might have just one of these prototypes around, and you just can clone them, right? As opposed to having to have each one of these factories 4 different levels of abstraction, right? So the prototypes, to avoid hierarchies that parallel the products. So in prototype, you have a prototype, a base prototype that has a virtual clone function, right? That's not implemented, right? It doesn't have any implementation. Instead, it's implemented by some derived classes that inherit from the prototype, right? And they themselves actually implement the clone function that allow you to copy these instances, and right, that each one actually implements the clone. Each one will be cloned differently, right? Because each concrete function class will either have to do a shallow copy, or maybe has to do a very deep copy, right, of all the objects, especially if you have nested classes within classes within classes, or arrays of objects, right, or lists. You'll need to iterate over that and reinstantiate all that to clone. So clone would encapsulate all that logic. Some concrete types, prototypes might need to, before you do the clone, you might need to provide some initial parameterization, again, without avoiding calling new, right? Instead, what you do is that you initialize this first instance, and then you call clone on it, right? As opposed to calling new and passing the parameters that you would pass to the initializer, right? And then the client would get a prototype, right? That is the abstract class instead of any concrete ones. So prototype declares an interface for cloning. The concrete prototype is the one that implements the cloning itself, and the client just retrieves only the abstract prototype product. Allows to be able to reinstantiate these things at runtime, right? So that you don't have to reinstantiate using new, and allows you to also, if you have other objects at runtime that implement the same interface, right? You can load them dynamically. Either in Java you would do something like class.forName, right? and you can give it dynamically what class you want to load dynamically. If you know the package and the name and the fully qualifying name of the class, you can just load it, right? And as long as it implements the interface you want, you can load all these things. It'll search them through the class path, right? If it's available, it'll instantiate it and run and load it dynamically. So here's a very quick example of implementing the prototype. We have an interface called prototype that declares an abstract prototype clone function, so it does not implement it itself. Instead, you have a concrete prototype that implements the prototype interface, right? And internally, it implements the clone function. In this case, it's implementing super.clone, meaning it's using Java's own clone function. Right? So Java already implements a clone function, right? That it can clone itself. You can clone the current instance object, will just clone, it will do a deep copy. So internally, what you do is that when the client boots up and is running, it creates object 1 once and never again. Right? Because this new instance over here is very, very expensive, presumably. This is when that's when you actually use it. When it's very, very expensive to instantiate prototype, right? And then once you instantiate it, you never let go. Right? You cache it, you put it in some place, perhaps in a factory, right? And you can combine it with a factory. And once you want a new instance, you never call new on it again. You only call the object.clone on it, right? And this would be improve performance fairly well. So if we can apply the same idea to our Maze toy example, we can re-implement this by keeping in the factory, right? We can keep track of the prototype maze and wall and room and door, which are going to be passed to us as instances, and we're going to keep track of them here, cached in memory, right? So that any new time you ask us for a new wall, we wouldn't actually instantiate these, right? Instead, we would clone them, right, and give you a clone of the original wall, of the original maze or room. Door we'll need to implement initialize because its cloning needs to be parameterized. You need to say that this new door, right, connects these two rooms, right? So it needs to be the creation needs to be initialized. So each one of these maze and room and whatnot, the factory methods, right, that can be rewritten that instead of calling new on these classes, they just call clone on them, right? Whereas the door is a little bit different. It needs to first, it clones and then it parameterizes the values to be the values of the room that it's connecting, and then it returns the door instance. Maze clone. Here's the version for the maze, right? It instantiates the maze. And then it clones it. Here's the cloning of the room. Instantiates the room, and then it sets the values of each one of the sides. So notice that we're replacing all these factory methods, right, with versions that use cloning instead of instantiating these. Okay. All right. The driver. All right, Singleton. So Singleton is another design that's it's very useful, and again, it's widely used in industry and throughout many of these infrastructures. That oftentimes you want to make sure that you have a single instance of something, right? Of something that is the only the go-to instance. If you want to either connect to a database, or you want to connect to a network, or you want to connect to do some security or multi-threading or transaction management, that there's only one instance of these services going around, and everybody uses the same instance, right? Usually these are typically also objects that are fairly expensive to instantiate, and typically they're instantiated only once when the system boots up, right? And then it's kept around and shared amongst multiple folks, right? It's a very common design pattern when you're connecting to a database. Usually the driver manager that handles the connection pool is a singleton. The objects that that allow you to connect to a particular service, also typically there are singletons. And that if you want to connect to a remote service API, typically it's done through a singleton that you keep around and you share this reference going around. So singleton certainly is it's a very common design pattern, and typically they're implemented in Java by using the static using the static keyword, right? Typically what you do is that you make the constructor unavailable, right? So that you're not ever allowed to deliberately or inadvertently, right, instantiate these things, right? You can't call new on them, right? Instead, you expose a factory method, right? That is smart enough to know whether you already have one of these, right? If you already have one, I'll just return the one we already have, the one we instantiated earlier. If we haven't yet instantiated it, then we'll make an effort to instantiate it the very first time. Right? Typically, that first instantiation might be long running, right? So whoever has the misfortune of being the very first client to instantiate will have to wait a couple more milliseconds until this heavy object gets instantiated, gets loaded into memory, and then gets passed a reference to it, right? But subsequent queries, subsequent accesses to the singleton will be much more performant, right? Won't have this overhead as the previous calls. So typically the implementation goes something like this, where we make the constructor private, right? So that we're not ever we're never tempted to call new on the constructor, right? So the constructor is not available. We cannot call it, but instead we expose a factory pattern that is static, right? That can only be called through the class itself, right? So that it would be Maze factory dot instantiate, right? Give me an instance, right? And in that instance, typically we check to see if a static instance, we only carry that one single instance around, right? That's going to be cached within this class as a static variable. We check to see if it's null. If it's null, then it must be the very first time that we're instantiating this, right? We call new, right? We can call new because we're static, and we can call we have access to the private constructor, and then we return the instance. Next time around, it won't be null. Right, so we just return the instance. It's a very, very common design pattern, widely used for services, for data access objects, business objects, or things that we just want to carry around and just instantiate once. And so from the client, we would use the static method, dot instance, and we return the factor, which we could then pass along to create the rest of the maze. All right. I think I'm going to leave it here.